Dear listeners, welcome to a new video. Today we will talk about validation and hyperparameters in LightAutoML. There are several types of validation in LightAutoML. One of them is inner k-fold validation, which helps to generate out-of-fold predictions for the training set. These are non-overfitted predictions which are passed to the models on the next level for stacking. The predictions for each training fold are made using a model trained on the remaining folds. The prediction for a test object is an average of all k-fold models. Furthermore, validation is required for hyperparameters tuning. Additionally, the user can specify which validation type to use for model evaluation. One possible option is a holdout validation set. This type is especially useful if we expect the distribution of data to change after training, and we want to test our models on slightly different data. The other option is k-fold cross-validation used by default. Finally, the user can provide a custom validation split, for example, a time series split, as shown on the slide, where we train on the previous events and predict for the following events. Common holdback you might face is nonce in the out-of-fold prediction for the training set. Such a thing may happen if some of the objects have never been used in a validation sample. This may occur in a custom validation, for example in time series split, where the leftmost part of the data never appears in validation. Another possible scenario is that the AutoML didn't have enough time to fit some folds due to time limits set by the user. It would be wrong to say that our out-of-fold predictions are not overfitted at all. The overfitting might happen because of hyperparameters tuning. A possible solution is nested k-fold cross-validation. The main idea is to further split each of k-folds into training and validation and use this microsplit for fitting hyperparameters. However, nested k-fold is disabled by default, as it did not show a quality increase on benchmarks in the experiments held by the developers. Now, let's discuss the hyperparameters tuning in LightAutoML. There are several ways presented. The first one is during model training and early stopping. Early stopping is used for the number of trees in gradient boosting and the number of epochs in neural networks, which are trained in the NLP preset. The second option is expert systems, consisting of predefined sets of hyperparameters. Some hyperparameters require more intensive search, and thus sequential model-based optimization is used. This algorithm is an example of Bayesian optimization, similar to the Aptuna library. Finally, some hyperparameters can be effectively fitted with the grid search. Such parameters of gradient boosting, like learning rate or number of leaves, are selected according to some expert rules. An example of such is presented on the slide. Expert parameters might be far from optimal, but recall that we use an early stopping for the number of trees. Combining these techniques often gives a good result. Generally, we start with training a baseline with expert hyperparameters. If enough time is left, then a more thorough search is applied. Turns out that the larger the dataset, the smaller the gain from tuning hyperparameters, which is good because we can afford many trials for small datasets and cannot for larger datasets. Tabular AutoML uses the tree parser estimator, or TPE, algorithm from the Aptuna framework for gradient boosting hyperparameters. At each iteration of the algorithm, we approximate the dependence of our quality metric on hyperparameters by some surrogate function. Then, we choose a new set of hyperparameters, optimizing the surrogate function. Next, we train a model for this set, save the value of the quality metric, and go to a new iteration. Grid search is an effective technique for fitting the regularization coefficient in a linear model, because we can use early stopping after the quality on a validation set stops improving. Moreover, warm restarts are really helpful. Proceeding to the next value of the regularization coefficient in the grid, we initialize the weights with an optimal solution from the previous iteration, which speeds up convergence. LightAutoML supports several levels of models, allowing to create arbitrarily deep stacking ensembles, but they are of no practical use. By default, two-level pipelines are used only for multi-class classification. In experiments carried out by the developers of LightAutoML, stacking made an improvement for multi-class classification, while the metrics for regression and binary classification stayed the same. Blending is an ensemble of last-level models. This is an extremely simple model which does not overfit at all, and thus does not require any validation set. Blending can do model selection, dropping out unnecessary models, speeding up the inference. There are three possible blending strategies. Select the best model and drop the rest, do simple averaging of models, or take an average with trainable weights. The weights are fitted with their coordinate descent, and models with the weight close to zero are dropped. Tabular AutoML has a minor drawback in terms of benchmarks quality. It fits fast, and therefore loses to competitors, which utilize all available time. This happens mainly on small datasets, and we remember that hyperparameters tuning is important for such datasets. The solution is tabular utilized AutoML, which blends tabular AutoMLs with different configurations and cross-validation random seeds. At first, it seems that this is useless in terms of overall quality, but turns out that such a trick can lead to a quality improvement. In this video, we have discussed validation schemes, hyperoptimization, and ensembling in LightAutoML. Thank you for your attention.